Our next to last speaker in the, I'll let Steve get out of the way here.
Sorry about that.
Here, hang on. Next to last speaker is Sahand Hormoz from Harvard, who is going to tell us more about the search.
Thanks a lot, Charlie. Let me thank the organizers first, especially Keith, for inviting me to this wonderful workshop. So I'll talk about similar ideas as Steve, and actually you gave me the perfect segue. So I'll talk about core deformation in 3D, and if it's possible to avoid it. And also I'm going to start from the singularity and move backwards. So I'm going to forget about the initial conditions. So that's going to be the essence of our work here. And this work was done with Michael Brenner, who was my advisor at Harvard. Okay. So these are the Euler equations, and what they are, they basically describe the flow of a fluid if you can neglect viscosity. I'm also going to assume that the flow is incompressible. Just a bit of notation, the capital D is going to denote convective derivative. So I'm not interested in the question if physically these equations correctly capture how fluid flows. I'm interested in the mathematical question if they're self-consistent. So if you give me a nice set of initial conditions, are the solutions going to be well behaved for all later times? Why should you care about this problem? Well, as was mentioned, this is one of the 7 problems that the Clay Mathematical Institute proposed, for solving which you would be awarded $1 million. And I would say probably 1 million is still a lot of money to a postdoc. And so there's a Poincare conjecture in this list, which has been solved. There's P versus NP, Riemann hypothesis. And number 6 on the list is a problem that's known as the existence smoothness condition in the Navier-Stokes equation. And you would get the money if you can show that for 3D Navier-Stokes equations, if you have a nice set of initial conditions, your solutions are going to remain globally defined and smooth for all later times. And that has to be true for any set of initial conditions. I agree with Steve in the sense that I don't like Navier-Stokes here. I'm going to focus on Euler. That's probably a better problem. And I'm going to focus on counterexamples. That's more, I guess, easier for an applied math person to do than giving a rigorous proof. A nice abstraction to use is instead of thinking of velocity field is to think of vorticity. Which obviously is just a curl of the velocity fields, and it corresponds to infinitesimal rotation of your fluid elements. And it's nice because if I take the curl of the Euler equation, I can get rid of my pressure term, which is a non-local term in my velocity field, and it's hard to deal with. If I do that, I get my vorticity equation. And if I want to write this in a self-contained form, I want to describe my velocity in terms of my vorticity. I can do this in analogy with magnetostatics, because this equation looks like an equation that tells me current is just the curl of the magnetic field. So if I want to do this in reverse, if I want to calculate what my magnetic field is given a current field, I just apply the Biot-Savart law. I can do the same thing here. If I want to evaluate my velocity at some point x, I can just apply the Biot-Savart kernel over my entire vorticity field. And this kernel basically has just a inverse cube dependence on separation distance between the 2 points. And the question I'm going to ask now is there singularity in my vorticity field? And you can see, I mean, it looks promising. There's definitely nonlinearities here on the right-hand side. So there's nothing that a priori is ruling out the possibility for singularity. Okay. The mechanism I'm going to focus on, again, as introduced by Steve, is going to be stretching of vortex tubes. Vortex tubes are basically cylindrical objects where vorticity is everywhere 0 except for the inside of my tube. There's a nice conserved quantity, which is circulation. If you just integrate your velocity field on a closed contour around your tube, and this quantity has to be conserved. You can also think about this by applying Stokes' theorem as just integrating the curl of the velocity or vorticity along the cross-section of this tube. So if I take one of these vortex tubes, and if I squeeze it in the middle, again, as suggested by Steve, let's say I squeeze it so much that the cross-sectional area halves here, then to conserve circulation, my vorticity has to double. So the question is, can we do this in a singular way? Can I squeeze it so much that my vorticity becomes singular in finite time? And as you saw, these creatures are nice objects because first of all, they're physical, so they flow with my velocity field. And also, if the flow is incompressible, they're going to conserve volume. So that's why the ends here had to bulge when I was squeezing the middle. Okay. Yeah, so the question again is, can we squeeze at a sufficiently fast rate to get a singularity in vorticity? Of course, I mean, these objects can have complicated dynamics. They can flatten, form sheets. But I'm going to assume that this is not allowed. So that's just going to be the assumption here. I want to be able to basically characterize the geometry of my tubes, the cross-sectional geometry, always using one length scale that I call sigma. So this is basically the diameter or the thickness of my tube. And I'm going to preclude the possibility of these guys flattening into sheets. So basically, at all times, I want to be able to say that this length scale sigma, the thickness of my tubes, is smaller than all the other length scales in my system. And what does this mean? It means, well, basically now I have a nice one-dimensional problem. Again, as Steve was talking about. So, and it's easy to characterize the shape of these tubes now because it's just one line. I can parameterize them in terms of some arc length parameter. And for every point along my tube, I'm going to associate also a thickness, so the sigma. And I can think of dynamics. So these guys can change in time. And I'm going to distinguish the dynamics between the shape of the filaments that I call outer dynamics and the change in thickness of the tubes. So if these diameters are getting larger or smaller. So if I'm squeezing these guys or letting them expand. And then I'm going to show you that these outer and inner dynamics are coupled. So obviously, they affect each other, but they're only weakly coupled. So it's through a logarithm. So it's kind of, it makes sense to separate the two.
So what's R?
So R is describing basically the shape of my filament in space.
So R is a vector.
Oh, absolutely. So R is a vector. This is a scalar. Sigma is a scalar, yes. Yeah, so to be perfectly clear, so this is a vector, this is the arc length parameter scalar, this is time, this is another scalar, which is only defined along this guy here. Okay. So how do I find dynamics of this guy? How's the shape changing? I just apply the Biot Savart kernel, but now I'm integrating along this line. So now something interesting shows up. It turns out the filament is going to induce a velocity on itself. And there were, I guess, many talks a few days back on this. And this velocity is going to be proportional to the logarithm of the radius of curvature to the thickness of the tube at that point. So here, in this basically comes off from a cutoff that I'm putting in my hand. It's going to point in the binomial direction, but this is just details, so if you don't know what binomial is, it's not important. This velocity, this term here, the self-interaction term, I'm going to call alpha. It's important. We're going to come back to it later. So this is going to give me the dynamics. This velocity is going to tell me how my filament is moving. Now, I can also calculate this stretching. This is exactly the equation that Steve showed us. So there's going to be this external velocity is moving my filament, is also stretching it. But the stretching is going to come from the normal component and also the gradient of the tangential component. So if they have 2 points that are infinitesimally close, they're going to move by changes in the tangential velocity. And obviously, I told you that the volume is conserved. So if I stretch, let's say, by a factor of 2, my cross-sectional area has to go down by a factor of 2. And here you can see the coupling. So this external velocity field is changing the shape. It's going to change my, through the stretching, it's going to change my cross-section, the diameter of the tube here. But that's going to come back here and couple to the velocity that the filament is inducing on itself. But it's only coupled through this logarithm. So it's not a very strong couple. Okay. So now I can actually do simulations. I can take this approximation, the filament approximation, and for example, take the famous conditions by Bob Kerr, the initial conditions, and run them for 2 anti-parallel vortex filaments. What I'm plotting here is the curvature at the tip of the filament. So you can see the curvatures actually went up by 10 orders of magnitude. So these guys became sharper and sharper at their tips. So that was a promising sign. And also the tips came closer and closer by 10 orders of magnitude. So you can see there's a good chance that maybe we stretched this guy enough to have gotten a singularity. But if I run the same simulation and plot for you the tube diameter right here at the tip, you can see that it only changes by a factor of 2 or 3. So the 10 orders of magnitude change that I got in separation distance and increasing also the curvature obviously was not consistent because I violated this assumption. So these things would have hit each other way before, very early on in my simulation. So I didn't get much increase in my vorticity, so maybe only a factor of 10. So this assumption was not valid. And if you had done the full 3D simulations, like done by Tom Howe, you would have seen that these guys would have flattened. So this was the core deformation that Steve was talking about. They would have formed sheets, and the sheets would have rolled, and that would have stopped the amplification in vorticity. So the question I want to ask is, so how do we, I guess, find the initial conditions that can give us a singularity? I mean, you can do an exhaustive search. You can go and tweak the initial conditions and then run your simulations and hope that now you get a larger amplification in vorticity. But I mean, if you do this numerically, you might be screwed, as Steve said, if the initial conditions that correspond to singularity are unstable, and also exhaustive search is not very practical. So I'm going to give you an argument that why I don't think that any set of initial conditions that involve stretching of vortex tubes can give you a singularity. And this is going to, so this is exactly, I guess, what Steve referred to earlier on, is if we go now close to singularity and forget about the details of the initial conditions and ask the questions, well, what's going to happen if I'm infinitesimally close to singularity? What are my filaments going to look like, and what's going to be the dynamic behavior? A hint of what's going to happen actually comes if I, again, go and plot for you the separation distance between the tips of those 2 filaments that I showed you. You see there's a nice parallel, and basically the separation distance is going to 0 as the square root of time. You can say, well, this is not too surprising because the only dimensional variable that I have in my system is the circulation. It has the units of length squared over time. And so the only length scale that I can extract from my system is going to look like this. And obviously, this gives you the square root of time to singularity here. So T star here is a time where the alleged singularity might occur. So I can say, well, I can measure all my length scales now, this arc length parameter, in terms of this natural length scale of the system. And the ansatz that I'm going to impose is that the filaments, the shape of the filaments is going to look self-similar, arbitrarily close to the point of singularity. So if I'm asymptotically approaching the point that I'm going to get singularity, I can, instead of having this general form for the shape of filaments, I can write down a self-similar ansatz like this. So here we've gone from I guess, a PD formalism to an ODE. This is only dependent on this dimensionless variable A. Okay. And the key is that I only impose this on the outer dynamics. So this is imposed on the shape of the filaments. I'm not saying that the core size is going to 0 at the square of time also. That can have some arbitrary scaling. This is only the shape that's going to follow this ansatz. And the nice thing is that, well, this is the intermediate asymptotic limit, and you can give it the whole shebang that then now you don't care about the details of initial condition, you're just focusing on the mechanism. And this is what's nice about this approach. Okay, so for the core size, I'm gonna allow arbitrary scaling. So this guy, this P exponent can be anything here. But I told you there's a coupling between the inner and the outer dynamics. So I'll be able to calculate what this P is based on the shape of the filaments close to the singularity point. And we can say that, well, let's assume that a singularity exists. And this will actually require that P is larger than 1. I believe this is what Steve was talking about with the gamma quantities, but here I'm calling it P. So this basically ensures that the core radius is going to 0 faster than all the other length scales, so the filament approximation is going to remain valid. So then you can apply the filament approximation, then your singularity should be self-consistent. Okay, so how do we go and compute this P value? Let's take our ansatz and plug it into the outer dynamics, so the governing equations. That's easy to do. I'll get some complicated expression. The details aren't important here, but I can solve for the curvature of these filaments in similarity space now. And now I get an expression here. This is the remnants of the Biot-Savart law. Again, forget about the details. What's important that this thing is proportional to 1 over alpha. And remember, the alpha was a self-interaction term. It was the logarithm of the radius curvature over sigma. The radius of curvature is a length scale that's associated with the shape of the filaments. So it's going to go to 0 with the scaling, which is square root in time to singularity. The sigma here is going with this arbitrary scaling law, which I don't know. But by our assumption that P is larger than 1, alpha is going to infinity. It's going to infinity slowly, only logarithmically, but indeed it's going to infinity, which means that the curvature is going to 0. So these filaments are asymptotically flattening as they're approaching the singularity. You can show this explicitly if you solve these equations. This is what the filaments look like. And this 10th structure resembles, I guess, what Carlo showed us with his simulations of the vortex tubes approaching each other. But here, if you rescale this back into real space, you would get basically the famous tens of colliding filaments. So this alpha equals 1, this alpha equals 10, and you can see the flattening here. Just, I guess, for the experts in the audience, it's not easy to solve these equations, so we have to make some approximations. So we do LIA, but we do LIA with an extra term. So there is non-local contribution to the velocity, but the contribution only comes from one point, which is closest to the point that you're evaluating the velocity. Okay, good. What about the inner dynamics, the exponent P? That's the key to getting the singularity. So now I can put P into the inner dynamics equation and actually solve for it. And this is pretty cool. So this is the scaling exponent for the core. And here is a function of just the shape of your filament. So now I'm relating the scaling exponent to what these filaments look like in similarity space. And again, the details aren't important. And these shapes actually aren't universal. So they can change based on your initial condition, which kind of justifies this exhaustive search that people have done over various initial conditions. But what's key here, this term is proportional to the curvature in similarity space. Now, I told you this curvature is going to 0. So as I approach a singularity for all initial conditions, you can show that for this non-universal 2-parameter set of possible geometries that's allowed, P is going to go to 0, which is a contradiction, because we had assumed that this was 1. So it's not possible to, at least from what we believe, to get a self-consistent singularity. Let me generalize this a little bit, I guess, in the couple of minutes that I have left. We assumed that there was a self-similar structure arbitrarily close to the point of singularity. But I told you then there was a logarithmic time dependence. So this is not really self-similar. I was cheating. And you can say, well, maybe this logarithmic time dependence can save you. And these all show up as log corrections in real space. So they're very hard to go after numerically. But so if you want to be very careful, you have to basically write down a similarity PDE. So you don't really have an ODE. And so here I have this time dependence here, actually, to be more careful, this time dependence on the logarithm of the time to singularity. And again, I don't use an equality sign here because this equality is only true up to the shape of the filaments. So I can only compute the velocities, neglecting the tangential velocity, which leave the shape invariant. If you do this, then you can do some complicated math, and then you can get an equation for the dynamic behavior of that G double prime that I talked about, the curvature of your filaments. And here again, the details are important, but if you observe this equation enough, you see that this term is just a gradient of velocity field along the tangential direction, which in similarity space corresponds to the scaling exponent of the core, so which is basically that p-value that I was talking about. And we can't do this rigorously, but if it turns out that this equation is dominated by this term, you can convince yourself if p doesn't vanish, then you can satisfy the scaling exponent as set by dimensional analysis. So basically, any singularity that you get if for non-zero p is going to be inconsistent with the exponent that we'd expect from dimensional analysis. So if your only assumption is that this exponent has to be 1/2 for the shape of the filaments, then it's impossible to at the same time get a sufficiently fast stretching. Again, to emphasize, this is not a rigorous proof, but you can do roughly some counting of the degrees of freedom. It turns out, now besides the stretching criteria, the gamma larger than 1 that Steve was talking about, now you have 2 constraints. So you have to satisfy this guy to make sure that your curvature is happy, and then you also have sufficient stretching. And because you only have 2 degrees of freedom, the curvature and torsion along with filament, we think that this is at least very hard, if not impossible, to satisfy for any general configuration of vortex filaments. So to summarize, we simplified the dynamics of vortex filaments by separating the outer dynamics, the shape of the filaments, from its core. We focus on the mechanism, the stretching, rather than the details of initial conditions. And by analyzing the asymptotic limits, following what Steve suggested, by moving away from worrying about initial condition, by going asymptotic close to singularity, we were able to rule out, or at least say it's very unlikely that you can get a singularity by stretching a vortex. So let me stop there. I'll be happy to answer any questions.
Questions, comments, complaints? Yes, Keith.
It seems a very good idea to look for a singularity by assuming you found one and going backwards in time, particularly because the Euler equations are time reversible. And one can imagine assuming a structure with an epsilon going to 0, giving you the singularity. And for each epsilon, integrate back a little bit in time and see what you would have to start from to get to that. Is this roughly your philosophy?
It's the essence, and also with this added assumption that we enforce some form of self-similar structure very close to singularity.
I think that you shouldn't really do, because it's known that doesn't work.
Exactly. So, well, now let's be careful. So Chai proved that there's no strictly self-similar singularities to the Euler equation. So when I say self-similar, I mean self-similar of the shape of the filaments. So the core is following its own scaling. So first of all, it's not strictly self-similar. And second of all, then we believe the dynamics that are going to come in close to the singularity are going to be log time dynamics of the singularity. So you can think of it as not self-similar, but really slow, sluggish change in the shape as you're approaching the singularity. So in a way, you can do a transformation, not to the similarity space, but to a more space better suited for analyzing what the stretching rate is going to be. But you're absolutely right. I mean, there are no strictly self-similar singularities to the Euler equation. That's no.
I just wanted to add that in the moving line problem I was talking about, again, that is also self-similar in an expanded sense of having 2 different, so it's not uniform in the sense of Chai. Thank you for that.
David?
Can you relate this to previous work? For example, how does this relate to the work Rich Peltz did in?
Oh yeah, Peltz is a good question. So unfortunately, I have to say from this, I would say Peltz was wrong. So this octahedral symmetry, or however convoluted kind of symmetry you want to propose to ensure that you're going to get singular stretching, I don't think it's possible.
Why is he wrong?
So we believe that, I guess given our results here, that it doesn't matter how you play around with the geometries, that you're not going to be able to beat core deformation.
You're not going to be able to do what to the core?
So the core deformation is basically going to get you. So now you're not going to be able to achieve a singularity where the filament approximation holds.
Or you say you can't ignore core deformation.
Absolutely, yes.
That's what. Okay.
But you're talking about the filament approximation here.
Yes. Wait, no. So I'm sorry. So let me clarify. Actually, Bob is this important. So there are singularities that are proposed where you form sheets and you roll, and you still get amplification of vortices. So we're not saying anything about that. We're saying as long as, yeah, the filament approximation holding in only the stretching of the tubes. So that's a mechanism for singularity.
So what happens if you do, again, the reconnection, if you set up a reconnection geometry instead of this thing?
They'll flatten and roll onto each other. They
It's
form
gonna be
sheets.
yeah, okay. So this local analysis applies to anything.
And sheets aren't that great because at least we believed initially doing this work that if we can get the singularity using just stretching of tubes, then this might survive addition of viscosity. So if you're really after the $1 million, then if you do find a singularity in the Euler equation that's due to the stretching of the vortex tubes, then you might be able to find the same singularity for Navier-Stokes.
Okay, anything else? Okay, moving right along.